arc seconds in RC 10^-16. And so this is the interstellar radiation field, and this is just a radiation field at black body temperatures going from 2100 to 2600 in terms of photon fluxes. And of course, if you have cool black bodies, you don't have highly energetic photons coming out. This is calculated at 50 stellar radii. You don't have high energy photons. So if there are black body-like photons coming out of these objects, their influence on the chemistry is very selective. There may be some molecules with weak bonds that they can break, and other things with strong bonds that they can't affect. And this is just a table I made up just to show that the molecules in red. So these are the unshielded, the rates at 50 stellar radii without taking dust into account. And I just wanted to compare these rates to interstellar unshielded photo rates, which are around 10 to the minus 10 or 10 to the minus 11 or so. And for some molecules, we find that these kind of low energy photons can break them very easily. And so you get rates that are much enhanced over their interstellar values by 3 or 4 or 5 orders of magnitude. And other molecules that aren't affected at all by the photon field, where their photo rates are much lower than the interstellar rates. So there's a very selective effect goes on in these envelopes. And again, we looked at what happened here. So it turns out that you have so much dust at high mass loss rates that the dust absorbs all the photons, even if you make very clumpy models to make the material as porous as possible, so to let the photons escape. So at 10 to the minus 5 solar masses, so nothing very much happens.
How do you do that radiation field for the star? You
Sorry?
assume that there is a spherical.
I'm only assuming, yeah. I'm assuming that there's a
spherical photosphere, and then you're putting the clumps outside. Is that?
Yeah.
That's
right.
how the calculation.
Yeah, that's how the calculation works. Yeah. So again, you can get again changes to at low mass loss rates. At least for these photons, you can get again differences in abundance that can be quite significant over the kind of smooth models. So these photons could have, in fact, they're very, very selective. I just want to finish by talking about kind of another complication that's really been clear in the last couple of years, and that is the presence of really structures and asymmetries in these objects. So this is a carbon monoxide map from Terncharo's group, where you see in CO2 to 1. So this is the rings around RC 10 to 16. What they have fitted these structures to is a spiral arm, and argue that there's a binary driving this. So if you look at the distances typically between these rings, they're typically separated by, if you take the mass loss, so the expansion velocity of the material, by about 800 years. And so they've argued that this is driven by a companion, which is orbiting at a distance of about 100 AU. There are other observations that show, again, as I mentioned before, again on very small scales, close to the photospheres. So this is in an RC 10 to 16. This is a sodium cyanide spectrum. So these are the individual transitions, but they've stacked them in here just to make them look cleaner. Again, material being very clumped. And again here, RC 10 to 16, where in red sodium cyanide, and which is clumped in the inner envelope, and then magnesium isocyanide, which appears in the outer envelope as one of these kind of shell distributions. So these objects certainly aren't spherical and certainly symmetric. And again, there's been lots of observations in recent years showing, again, this is observations of carbon-rich HB stars. So this is 12CO, 13CO, and this is HC3N. So again, you see these kind of spiral structures, very beautiful structures coming out. But there's also evidence for disks in some objects. So this is Puppis, which in the optical 645 nanometers shows a very nice disk in this structure. But if you look at silicon monoxide, you see blue and red shifted emissions separated around this. This is a rotating disk. So there's there's lots of structures in these. And I just want to finish by saying a few words about a program called Atomium that Carl Gottlieb and I are involved in. So this is a Millar project which is trying to understand the origins of dust and molecules in oxygen-rich stars. So we're looking at very high resolution at a number of oxygen-rich stars. And our aim here is really to try and understand how the precursors of dust, where they are, if it can tell us anything about the dust formation process. And so people have put together schemes which try and convert alumina Al2O3 into some sort of mineral types of compounds. So this is an Millar program. It has 17 oxygen-rich stars that are a mixture of Mars, red supergiants, OHIR stars, and there's a couple of S-type stars, but carbon oxygen ratio is very, very close to 1 in there. And I think we've just had our last high resolution data in the last month. So the project now has all the data. Again, we're looking at very high resolution of around 25 milliarc seconds. So again, in terms of stars are different distances, but in the closest stars, in the order of a few stellar radii. So trying to really probe the dust formation and inside the dust formations. So what we find is stars are spherical. So all our stars, so structure, I can't tell you the names of these, but you see actually they look like planetary nebulae. So if we clean this up and put a picture of planetary nebulae beside it, you'd be hard pressed to tell which were the planetary nebulae and which were the stars. So we see all kinds of structures. We see spirals, we see density, equatorial density enhancements in these objects. We see lots of clumpy gas. And so a big challenge is to try and understand what's happening here, both in terms of the physics, why these structures arise, and how that affects the chemistry. So one of the members of the team, Ward Homan in Louvain, has been coupling a hydrodynamic code with a chemistry code to try and understand the processes that are occurring and where you can get these structures out. So he calculates what happens to the physics in one time step, and then goes and feeds those physical conditions into the chemistry and advances the chemistry by a time step, and then goes back into the SPH code and repeats the process. And so his particular calculations so far have been done with a companion of a solar mass at about 4 AU, distance from a central star at 1.2 solar masses. And he calculates the density and temperature. Again, you see that there's a little accretion disk forms around the companion, and then the spiral structure is driven. So he's got densities and temperatures at every point in his grid. And if he does that, he can put that into a simple chemistry model and see how the CO distribution looks like in this model. And he's got other pictures of water and OH and so on. So this is around assuming an oxygen-rich environment. So his model is very simple. He has no photons in it. His temperatures in the accretion disk are on the order of 10,000 degrees. So you certainly can generate ultraviolet photons at those temperatures. So I just did a little toy model again where I just looked at the effect of putting calculating the photon flux from a disk where I assumed I just had a Neptune mass and calculated the Hill radius, and assumed that I was getting, and that was at 6,000 K, and just calculating the photon flux and seeing what happened to the chemistry. So I've picked here so the color codes are just two different temperature distributions for the envelope. So dotted are C+, dashed is atomic carbon, and because I've been told there have been observations now of CH in this RC 10216, I've also just put in a CH distribution. But depending on, it's very sensitive to parameters, but if you make the material mostly interclump material, and you pack the clumps into small volumes, then you get lots of photons which destroy, in this case they destroy acetylene and HCM, which are abundant molecules close to the star, and convert into C+, and carbon. But as I said, they're very sensitive to parameters, but I make the flows look more like a uniform flow, so I make it more like a smooth flow. Then you see the distributions of atomic carbon and carbon plus look more like they do in the smooth case in the other reasons. This is also kind of interesting because I've been told actually that carbon plus has been detected now in RC 10216, but it's seen from the inner envelope, so not from the outer envelope. Atomic carbon is detected and detected in the outer envelope. There may be issues to do with excitation around here. Fine structure transition in atomic carbon has an energy of 91 Kelvin, and whereas the 490 gigahertz transition of carbon is at 23 Kelvin. So in carbon plus, you need certainly warmer, denser gas to see it. And so you may have lots of carbon. We know there's lots of carbon plus in the outer envelope because it has to become the interstellar medium, but it would be very hard to see. So it's just we're just beginning to think about whether photons from accretion disks like Ward is showing from a companion object, which is likely driving a lot of the structures in these objects, and play a role in the chemistry, or whether it's just external photons